Okay, so we are doing the HL level for atomic structure today. And so you had a couple of videos on here. A couple of them were the same. Well, or at least it covered the same section, but the information was kind of just a little bit different. So I went ahead and put both versions on there just in case you missed something in one, you'd get it in the other. And then kind of built into the notes, there's a kind of activity, and we'll kind of look because it has you do some practice calculations using kind of an online resource. And then we will talk about the last part where we have to kind of look at these graphs and talk about what do they mean. Okay. All right. So let me switch over from that to the iPad. Not really even sure why I should have just showed y'all Canvas. Okay. Okay. So towards the end of the SL stuff for topic 2, we have these line spectra where we can show if an electron falls, how much energy will basically be given off. And so it tells us what type of radiation. So like we have infrared, visible light, and UV. And so what the HL does is it kind of adds sort of a mathematical aspect to this. Because if I have an electron that falls from, let's say, from the first or the second energy level down to the first, like this, that's a pretty low amount of energy. So that's why it gives off, or I'm sorry, I just said it backwards. That's a high amount of energy. So that gives off UV radiation. If they fall from the fourth energy level, or they fall, sorry, I should rephrase that. If they fall down to the third energy level, whether it's from the fourth, the fifth, sixth, or the seventh, they produce lower amounts of energy, and so that falls in the infrared section on our electromagnetic spectrum. Falling down to the first level from any of these levels are higher amounts of energy, and that's in the UV radiation. The ones that fall down to the second energy level, these are the ones that they have just the right amount of energy that it falls in that visible light spectrum. And so for hydrogen, we get sort of a red, a blue, and kind of a blue indigo, and then a violet line that we see for hydrogen on its line spectrum. And so basically what the HL level says is that it basically starts off by saying, well, if we supply enough energy, then we can actually take an electron and we can promote it to the infinity level. And if you promote it to the infinity level, which it's labeled in this diagram, okay, it's n equals 6, and then it goes up to n equals 7, and then equals the 7's not labeled, but it's kind of there. But after 6, really, you go to infinity after that. And so what they're saying is if we put enough energy in that it goes all the way up here to where infinity is, then in reality, what's happening is that the electron's leaving the atom, okay? And it's no longer an atom, it's now an ion, okay? And so that's what it says. It says at this point, the electron has been removed from the attraction of the nucleus and the atom has been ionized. So it's now a hydrogen ion, okay? And so the term for that is ionization energy. That's one of our periodic trends that we learned last year. And so now we can kind of see like what is like, because we talked about ionization energy last year and how it trended on the periodic table, but now we can actually calculate it and we can actually see it in terms of atomic structure. And so you have your symbol, your equation like this. So you have an atom of hydrogen. It has to be in the gaseous form, okay, for ionization energy. That's in the definition from topic 3 from SL last year. And then when we remove an electron, we make a hydrogen ion still in the gaseous form. And then here's that electron that we removed, that we put up to the infinity level, okay? The last part on here, it just says that the amount of energy that's required to ionize it, it corresponds to the energy that the electron would emit if it fell back down from infinity down to the very first energy level, the ground state. And so basically, the energy difference between the infinity level and the n equals 1 level, we can measure that energy difference, or we can calculate it. And then we can use that sorry, we can use the frequency to calculate the energy. I misspoke. Okay. And so that's kind of what the next part talks about. It talks about there's two different equations. This equation is the speed of light equation. And so the kind of upside down y, that is the Greek letter lambda. And that represents my wavelength. The little thing, it looks like a V, but it's actually not a V. It's a Greek letter called nu, N-U. But that is the symbol that we use for frequency. Should have written that better. So if you know the speed, the wavelength of your light, you can calculate the frequency. And then once you know the frequency, you can use this equation to calculate the energy. And so the way that this works, the first equation, you'll always either solve for wavelength or frequency. Most of the time, the way ours is set up, we're going to be solving for frequency. And so the way that we'll use the equation is we'll always do frequency is the speed of light divided by the wavelength. Okay. There's a couple things to remember here. The speed of light is a constant. It is always the same. It is in your data booklet, I believe, on the first section where it has a bunch of constants listed. And it is this number right here, 3 times 10 to the 8th meters per second. Okay. Your wavelength, though, if you notice in this problem, your wavelength is given to you in nanometers, not meters. That's typical because waves of light are very, very tiny. So if we listed them in meters, the number would be a really small number. And so it'd be in scientific notation with a lot of, with a negative exponent. So typically wavelengths of light they're given to us in nanometers. So we have to remember to convert from nanometers to meters before we can plug that wavelength into this equation. Okay. So this is where you got to remember your metric prefixes because 1 nanometer is 1 times 10 to the negative 9th meters. Or you can flip it and you could say 1 meter is 1 times 10 to the positive 9th nanometers. So pick one and stick with that one so you don't mix them up. Okay. I tend to use the first one because I like the one to always be with the prefix. So I always say like 1 nanometer is 1 times 10 to the negative 9th meters. Okay. But as long as you put the number with the correct unit, you can use either one. So what you would need to do is, and I'm going to show you how to do it, but then it's going to be really easy in the long run. So if I know that my wavelength was 91.2 nanometers, and I'm going to use the first one. So I'm going to say 1 nanometer is 1 times 10 to the negative 9 meters. Okay. You can use a calculator. Okay. But you should be able to do this without a calculator. Okay. Here's how you do it. 91.2, I'm going to change that to scientific notation. So it's going to be 9.12 times 10 to the first power. Okay, everybody with me? 9.12 times 10 to the first, because I just moved the decimal one place to change it to scientific notation. Then I'm multiplying by this number. And if you guys remember, when I multiply numbers that are in scientific notation, I add their exponents. So essentially, I'm multiplying 9.12 by 1. So that gives me 9.12. I do my times 10. And then I'm going to add my exponents. So I have 1 plus negative 9. 1 plus negative 9, that's negative 8. So you should be able to do this without a calculator, but because if it's like multiple choices, then you won't have that. Okay. So that's converting from nanometer to meter should get to where, it's easier to do on problems like this. And so now it's in meters. So 9.12 times 10 to the negative 8 meters. Once your wavelength is in meters, then you can go back up here and you can plug it into this equation to solve for frequency. And so that's basically what they've done here that's already typed out. They didn't rearrange the equation first. I personally I like to rearrange the equations before I plug my numbers in. That way I have everything set up right. But you can do it this way. They did it to where they left the C over here, and then here's the wavelength that they converted to meters, and then they just divided it over. Okay, so that setup is what I have here. Okay, so speed of light divided by the wavelength in meters, and when you divide those in your calculator, you do get this number. It's a pretty large number. It's to the 15th power. And frequency, you're going to see potentially two different units for frequency. Frequency is inverse seconds. So you'll see seconds raised to the -1 power. The other one you might see for frequency is hertz. It's a capital H and a lowercase z. The number doesn't change. So like if I have 3.29 times 10 to the 15th inverse seconds, I still have 3.29 times 10 to the 15 hertz. Okay. It's just, they don't always like using the inverse units. And so they came up with a new unit for frequency. But IB tends to use that inverse seconds because we know they like their inverse units. Okay. So once I get the answer for frequency, then I use my second equation to calculate the energy, and that's going to help me calculate this first ionization energy. So I'm going to clear off some space down here so I can work out the other stuff with y'all. Okay, so once I have my frequency, the other equation, I'm calculating energy. Here's where I put frequency, the V or the nu, it's really nu. H is like speed of light, it's a constant. H is called Planck's constant, and it is this number right here, 6.63 times 10 to the -34. That's Planck's constant, and that's also in your data booklet, that if you can look it up if you need to, okay? So all you do is you take your answer that you got for the frequency. So we took, here's my answer to the frequency, we plugged it in to that equation, we multiplied it by H. H is always the same number. When I multiply them, here's what I get for the amount of energy. 2.18 times 10 to the -18, and energy is going to always come out in joules. If you want to see kind of the units of it, frequency is inverse seconds, and then Planck's constant is joules times seconds. So when I multiply them, the seconds cancel out, and I'm left with joules. Okay. Here's the thing, though. That's energy. That's not the ionization energy. Okay. So there's a couple things I need to do. Number one, remember our definition for ionization energy, it's per mole of electrons, right? And so when I get the answer for energy, in order to make it fit my definition for ionization energy, I need to multiply it by Avogadro's number, because that's going to give me how much for 1 mole of electrons. Okay. So that's all they did on this last step, is they took the energy they got, that's for 1 electron, and they multiplied it by Avogadro's number to get the amount of energy for an entire mole of electrons. So now you notice it's now per mole over here. The other thing, if you notice, they converted it to kilojoules. So they kind of did this all in one step, because what's going to happen is you're going to multiply Avogadro's number by this number. It's going to be a pretty large number of joules. And so you divide by 1,000 to turn it into kilojoules per mole. Okay. And that's pretty much what you're doing on some of the practice problems down here. It has kind of some definition and some other questions, but then here, like on number 4, it says the convergence limit for the sodium atom, it has, here's the wavelength, it's in nanometers, so you're going to have to convert it to meters. And then it says calculate the first ionization energy of sodium from this data. Okay, here's the 2 equations you need, here's Planck's constant, and here's the speed of light. So they've given you all the tools you need. You're going to have to convert this to meters. Then you can plug it into that speed of light equation and calculate the frequency. Once you have the frequency, plug it into the energy equation and solve for the energy. And then once you have the energy, multiply it by Avogadro's number to convert it to the definition for ionization energy being a mole or per mole. And then divide it by 1,000 to convert it to kilojoules per mole, because ionization energies on the periodic table, they're always reported in kilojoules per mole. Because if we did joules, the numbers would be really big. Because this one, it's already big, this example up here, because 1,310 kilojoules, if I left that as joules, then it would be, it'd be like a million, I think. 1, 2, 3, yeah. It'd be like 1,310,000 if I left it as joules. Okay. And that's too big. I don't want that. We don't like all those zeros. So on problems like this, that's basically the process. Okay. Change the wavelength to meters if it's not already in meters. Use the wavelength and speed of light to calculate the frequency. Use the frequency and Planck's constant to calculate energy. Multiply your energy by Avogadro's number to get the energy per mole, and then divide it by 1,000 at the end to convert it to kilojoules per mole. What you're doing here on this next page is you're basically practicing that process using some actual data. So there's a link, and I put it on Canvas, and it says you're calculating the ionization energy from the convergence limit. So it wants you to do hydrogen first. So it tells you to click on hydrogen. And then once it comes up, you're going to see a screen similar to this menu. And it says click on the energy levels. You want to make sure you're clicking on the energy level that's under neutral atom. Okay, on hydrogen, that doesn't really matter, but it will on your other ones. And then it says scroll to the bottom of the table. When you get to the bottom table, you're going to see the word limit. That's indicating the convergence limit. This number over here is what you're going to use. It's called the wave number. That's different from wavelength. Okay. And so it tells you here you can convert wave number to wavelength by just taking the reciprocal. So just do 1 over that number. So 109,678.7717. So do the inverse, do 1 over that number, or the reciprocal, I should say. That will give you the wavelength. Okay. Now, this wavelength is going to come out, I believe it comes out in meters. It doesn't come out in nanometers. So on this one, there's no need to convert from nanometers to meters. Okay. Because they didn't give us nanometers in the problem. We looked this up on a table and used the wave number to convert, and it's already in meters. So on number 5, you're doing what we just looked at on the example. Okay. It says now that you've calculated the wavelength, you can calculate the ionization energy. So number 1, it says convert wavelength to frequency. So that's using that speed of light equation. So you're using speed of light and wavelength to calculate the frequency. I don't know why it says the word below here, but you're using the energy equation, multiplying Planck's constant by the frequency to find the energy to remove 1 electron. And then the last thing it says is to multiply by Avogadro's number or Avogadro's constant to get the energy for 1 mole. And it doesn't say this, but you should always at that last step divide by 1,000 to make sure it's kilojoules per mole. Okay. After you do hydrogen, as an example, it says choose 2 other elements. You can choose whatever 2 you want, as long as they have data on there. Okay. And you're doing the same exact process using that method. And it does say, just a warning, like I said, for elements other than hydrogen, make sure you click on the energy levels under neutral atom. You don't want the one that's already been ionized once. That's going to give you second ionization energy, not first. Okay. So I know Princess had already started trying to work on that yesterday, so we'll come back to that and we'll kind of see if we can answer whatever questions you had. But I want to kind of finish this first before we do that. Okay, so the last part of this is sort of some graphical evidence. Okay, so this graph here, it has the successive ionization energies of aluminum. So successive means like they're all happening in a row, one right after the other. Okay. So what this graph is showing, if I look down here on the x-axis, it's the number of the ionization energy. So that means like which electron am I removing? Okay. So down here, I'm removing the first electron. Then I'm removing the second electron, then the third one, all the way up. And it ends, since I'm talking about aluminum, when I get up to here, I believe this should be number 13 all the way up here, because aluminum's atomic number is 13. It's got 13 protons and 13 electrons. And so this is showing us the amount of energy. And so notice that it's actually got a logarithm of the ionization energy. But what it's showing us is it's showing us as we take away more and more electrons, what happens to the amount of ionization energy that it takes to remove those electrons? Well, you can see kind of the general pattern is that it's increasing, right? The general trend is it's going up. Okay, it's a positive slope overall. There are a few like areas that are not exactly correct, or like, and they're not exactly in a straight line. Okay. So that's what it says here. It says these electrons are removed from the energy level furthest from the nucleus, n equals 3. And so they require less energy to remove because there is a lower attraction to the nucleus and more shielding by the inner electrons. So these ones up here, that are labeled 1, those are the 3 valence electrons that aluminum has. Okay, so that's why they're basically going up. Okay, after the second one, or I'm sorry, after the third one, if you notice right here, there's kind of a bigger jump. There's a bigger jump right here. Okay, it's still going up, but it's up a higher slope, or it's a steeper slope than between the first 2 electrons, or the first 3 electrons. And the reason the slope is a little steeper there has to do with our electron configurations and where the electrons are located. And that's kind of what this next section here on number 2 says. It says these electrons are therefore removed from the second main energy level. And it says, notice the jump between the third and fourth. This is evidence of the existence of energy levels. So because there is a jump right here, that proves that energy levels are a thing, because like we can't see atoms, okay? And there are some powerful microscopes that can see the outer edges of atoms, but we can't really see inside of them. So like, how do we know that there are energy levels? Well, yeah. I'll refill this out. I'll just let you fill it out here. I'll sign it and I'll let you fill it out. Yeah, that's fine. So because there's a jump there, that proves that there's a difference in energy levels there. Those first 3 are on the valence shell of aluminum, which is the third. Then there's a jump. And then if you notice the next like big bit, like all these right here in the middle, these all pretty much go in a straight line. The slope looks pretty much the same there. That's because all of those, they're all on the second energy level. Okay. And then if you notice after that, after there's, I believe, 8 there, because the second energy level is filled with 8. So there's 8 in a row there. And then there's another jump right here. That's because now these last 2, these are the ones that these 2 are on the first energy level. So that's why there's another jump. So the jump between the third and fourth ionization energies, and then the jump between the, let's see, was that 4, 5, 6, 7, 8, 9, 10, between the 11th and the 12th, those are because of energy levels. That's kind of our proof that energy levels exist. And that's kind of what the third section here says. I kind of already summarized it, but these are removed from the energy level closest to the nucleus. They require the most energy because of the strong attraction from the nucleus. There are a couple other things though. If we zoomed in on this graph a little bit and we just looked at the ones that are in the second energy level. So I'm going to zoom in on the ones that I highlighted in pink right here on this graph. So this graph up here where I highlighted them in pink, we're going to zoom in on that one section. Because if we zoom in, we see that they're not all totally in a straight line. There's actually some little differences again. And this one has to do with the fact, not that there's different energy levels, but this is proof that we have sublevels, that we have like the P and the S and the D sublevels. Because when we zoom in, what we see is that these 6 electrons are pretty much straight in a row. But then up here, there's a big jump before these last 2 right here. And so it's kind of labeled here on this graph, but these first 6 electrons, those are in the 2p sublevel. So they all require about the same amount of energy to remove, okay? There's a big jump here because now S sublevel is closer to the nucleus than P. So if you think about when we do our electron configurations, we start with 1, the first energy level, and it's 1s. Then we go up to the second energy level and we start with 2s, and then 2p comes after. That has to do with their distance from the nucleus and the amount of energy required for them. So what's happening here is that these 6 electrons are in the 2p sublevel. The 2 that I highlighted in green are in the 2s sublevel. And that jump right there is sort of our evidence that there's a big jump in the energy required. And that's what it kind of says down here, is it says between the 9th and 10th, it occurs because the 10th electron is from the 2s orbital and it's closer to the nucleus. So it's got a stronger attraction from that nucleus and it requires more energy to remove it, okay? There's also, if you pay close attention, it's really hard to tell sometimes if you're not totally looking at it. But if I look here between 6 and 7, it's a little bit steeper between 6 and 7. It's not exactly straight, okay? And the reason for that is this second bullet down here. Between the sixth and the seventh ionization energies, the reason there's a slightly bigger jump is because the sixth electron is removed from a doubly occupied p orbital. So what I mean by that is if I were to draw out, so I'll just kind of draw a box here. So p orbitals, remember they have, or p sublevels have 3 orbitals. And so if it's full, it looks like this. Oops, let me redo it. Let me switch colors here. Okay, so if the p orbital or the p sublevel is full, every orbital will have a pair of electrons, okay? And so if I draw the 2p, if it's full and it's got all 6 electrons, it's going to look like this. Each orbital has an up and a down because it's full. So if I start to remove electrons from that p sublevel, then what happens is the 6th one is removed from, so the first one, or sorry, the 4th one, okay, let me come up here. So this is the 4th one, this is the 5th one, and this is the 6th one. I want to make sure we understand what I'm doing before I show you all this on the diagram. So that's 4, 5, and 6, okay? Those are going to be the ones that are pointing down. So I would take away this one. That's the 4th one, because remember the first 2 were from, or the first 3 were from the 3rd energy level. Okay, so we're looking at just the 2nd energy level. So the 3rd electron, or the 4th electron would be that one. Here's the 5th one, and here's the 6th one. So the 4th, 5th, and 6th ones, that's all pretty much in a row. It's after 6, it's between 6 and 7 where there's a slightly larger jump. And then up here, 7, 8, 9, they're all pretty much in a row. The reason it's between 6 and 7 is because once I remove 4, 5, and 6, when I go to remove number 7, it's this one over here. And it's now in a singly occupied orbital because I removed the one that it's highlighted in purple. And so because if your orbital is doubly occupied, then the 2 electrons are repelling each other. And if they're repelling each other, it's going to be easier to take one of them away. Once I take that one away, if I want to take the other one that's still in there, it's going to require more energy because now it doesn't have another electron repelling it. And so what's happening on this graph is that these 3 right here, these are the 3 that are taken when they're doubly occupied. These 3 right here, these are the ones that are taken after each one's been removed, and now there's only a single in each orbital. And so there's a jump in energy in between because when you go from all the doubles to the singles are going to require slightly more energy because of the lack of that repulsion. Okay. The last one on here, it just has some graphs similar to what we looked at, and it's asking you to kind of explain and think which group it belongs to on the periodic table. And so what you want to look at on these is look at like the number of electrons, look at the number of ionization energies, and that's going to help you figure out, because if it's certain, if it has a certain number of ionization energies, you should be able to kind of figure out based on that, like its atomic number and things on the periodic table. And you should also be able to tell based on where the jumps are happening. Okay, because remember the valence electrons are going to be pretty much straight line, and then there will be a big jump between the valence shell and the next energy level down. So wherever the first big jump occurs, count the electrons before that. That tells you how many valence electrons it has, and that should help you figure out what group it's in. All right, so I'm going to go back up to our calculator.